Welcome to the Explainer. So today, we're pulling back the curtain on the invisible traffic rules of networking. You know, if you've ever just plugged a cable into a wall and expected it to instantly work, well, you're actually relying on some incredibly precise engineering rules running quietly in the background. We're going to unpack the raw technical mechanics of how our networks truly handle traffic. We'll be focusing specifically on how different devices manage data flow, and exactly why the setup that works perfectly in your living room would completely and utterly collapse in an enterprise environment.
It's a great question, isn't it? Why can't your home router run a corporate office? I mean, think about it. It gets you online, blasts out Wi-Fi, connects all your devices. It's super familiar. But as our sources show, while that standard small office/home office gear, what we call SOHO gear, is super convenient for, say, streaming Netflix, it actually has some fatal flaws when you try to scale it up. To really get why, we need to look under the hood at the absolute foundations of network traffic management.
Okay, let's dive into this. Here's our clear roadmap for today. Number 1, the SOHO network trap. 2, traffic jams, meaning collision domains. 3, loud noise or broadcast domains. And 4, segmenting for the solution.
Let's jump right into Section 1, the SOHO network trap.
To really appreciate the sophisticated solutions used in enterprise networking, we first have to clearly define the problem. And that problem? It starts with a typical SOHO architecture. SOHO networks rely on what's called a collapsed architecture. Basically, that just means a single integrated appliance, that little plastic box sitting on your desk, is actually combining multiple distinct logical functions into one physical chassis. You got your modem connecting to the ISP, your layer 3 router directing traffic, your layer 2 switch linking local devices, and your wireless access point for Wi-Fi. It's literally all just shoved into one single box.
What's really interesting here is how the exact things that make a SOHO router so convenient create an absolute nightmare scenario for an enterprise. First off, you've built a single point of failure, or SPOF. If that one box loses power or just randomly dies, every single function, internal switching, Wi-Fi, internet access, goes down instantly, zero redundancy. Second, minimal scalability. You're stuck with a fixed, small number of ports and a weak CPU. You can't just suddenly expand it to handle hundreds of users. And finally, limited segmentation. That router just lumps all local traffic into one single logical network, which makes managing security or prioritizing traffic basically impossible.
Which brings us to Section 2, traffic jams, or collision domains.
To understand why that single SOHO network chokes at scale, we actually have to look at physical traffic jams. A collision domain is the strict engineering definition for a specific area in an Ethernet network where multiple devices are competing for the exact same physical bandwidth. When devices share a physical medium, there's always a risk of simultaneous transmissions. Think of it like a narrow, single-lane bridge. If two cars try to cross from opposite directions at the exact same time, they crash, right? Well, in networking, if two devices transmit at once, their data frames literally collide on the wire and become completely corrupted.
So how did older networks handle this mess? They used a mechanical process called CSMA/CD, carrier sense multiple accessed with collision detection. It's basically a 3-step dance. First, the device literally listens to the wire. If it detects energy, meaning someone else is talking, it waits. If it's clear, it transmits. But if two devices jump the gun and transmit at the same time, they detect the collision, instantly stop, and wait a random amount of time before trying again. As you can guess, it's highly, highly inefficient.
And this inefficiency is exactly why older hardware, like Ethernet hubs, are a terrible choice for scaling up. An older hub basically operates as a logical shared bus. This means it creates one single massive collision domain for every single connected device. So if you've got a 20-port hub, all 20 of those devices are fighting for the exact same physical bandwidth. They're constantly pausing, colliding, and retransmitting. It's a mess.
Now, unlike a hub, an Ethernet switch separates collision domains port by port. Each switch port gives a dedicated connection to whatever device is plugged into it. So the crucial point is that in modern networks operating in full duplex mode, each port is its own isolated collision domain. This effectively eliminates those collisions entirely on that link. And routers do the exact same thing on every single interface, which beautifully solves our physical traffic jam problem.
But fixing physical crashes? That's really only half the battle. The contrast here is super important. A collision domain is all about physical layer 1 and 2 bandwidth competition, data literally crashing on a wire. A broadcast domain, on the other hand, is a totally different concept.
It's about logical layer 2 frame forwarding. See, while switches fix the physical crashes, they actually end up creating a massive logical noise problem. Moving on to Section 3, loud noise, also known as broadcast domains. If a collision domain is a physical car crash, a broadcast domain is like a logical shout across a crowded room. It defines the boundary of a network where logical broadcast frames are forwarded. A broadcast frame is just a message sent to a specific, all-encompassing MAC address. ff.ff.ff.ff.ff.ff. Imagine a guy walking into a packed room with a megaphone and shouting, "Hey, who has the keys to the company car?" Everyone in that room is forced to stop what they're doing, listen to the shout, and process it, even if they don't have the keys. The walls of that room, that's the boundary of your broadcast domain. Now you might be thinking, well, let's just turn off broadcasts. Actually, scratch that, you can't. These megaphone shouts are absolutely crucial for network survival. Essential protocols rely on them. Like ARP, the Address Resolution Protocol. It uses broadcasts to find the physical MAC address of a device when it only knows the IP. Or DHCP, which requests IP addresses. When a new device connects, it essentially shouts to the whole network, "Hey, I need an IP address to function." We need these broadcasts, for sure, but we desperately have to control them.
And this brilliantly illustrates our next problem. While a switch flawlessly separates collision domains, it does absolutely zero to stop broadcast domains. In fact, standard layer 2 switches will flood or forward all received broadcasts out of every single port, except the one they originally received it on. That means a single layer 2 switch defines the boundary of a broadcast domain. So if you link 10 switches together with 1,000 devices, one single ARP request is heard by all 1,000 devices. That sheer volume of logical noise will, without a doubt, eventually cripple your network's performance.
Let's hit Section 4, segmenting for the solution.
So how do we get the scale that our tiny SOHO router lacked while also controlling all that megaphone noise? Well, the ultimate boundary in a network is the router. Routers operate at layer 3, the network layer, and their golden rule is that they do not forward broadcasts. A router interface stops that megaphone shout dead in its tracks. Because of this, each router interface creates a completely brand new broadcast domain, what we usually just call a new subnet or network. By placing routers strategically, you're basically chopping that massive, noisy room into smaller, soundproofed rooms. Let's move to this next concept and see how this all builds into a perfect cheat sheet for your CCNA exam. Just look at how these devices handle traffic. The hub, no, and no. It doesn't separate physical collisions or logical broadcasts. It's just a dumb multiplier. The switch, yes, it separates physical collision domains per port, but no, it does not stop broadcasts. And the router, yes, it separates collision domains, and yes, it terminates broadcast domains. The router is literally the ultimate traffic cop. But here's the thing, in a real enterprise, we don't just use a bunch of physical routers to chop up these domains. We use something incredibly powerful called VLANs, or virtual LANs. A VLAN lets you logically segment a single physical switch into multiple isolated broadcast domains. So a broadcast generated by a device in, say, VLAN 10 is only forwarded to other switch ports assigned to VLAN 10. The rest of the switch ignores the shout entirely. It gives you incredibly granular control, and you still just use a layer 3 router to strictly govern any traffic passing between those VLANs. And this brings us right back full circle to our original problem, the SOHO network trap. The reason your home router can't run a corporate office is because true enterprise architecture relies on precisely segmenting these domains. By breaking up collision domains with dedicated switches and breaking up broadcast domains with routers and VLANs, we completely eliminate that single point of failure. We can suddenly enforce strict security policies between segments. And we get nearly infinite scalability, all because the network isn't choking to death on its own physical collisions and logical noise. So we've unpacked the foundational mechanics of how hardware physically and logically guides data across the wire. But it leaves us with a pretty provocative question to end on. As our physical networks continue to move entirely into virtual cloud spaces, where the wires and switches are literally just lines of code, how are these strict hardware rules going to evolve next? Will the concepts of collisions and broadcasts even survive the jump to the cloud? Well, I hope this explainer gave you a rock-solid understanding of the mechanics running silently in the background of your daily life. Keep exploring, keep learning, and I'll catch you on the next one.